Hello, welcome to the Computer and Logic Essentials tutorial, video assignment 1 of character encoding. My name is Cheryl, also known as Yoko, as the first speaker of the video. Then later followed by Chaman as the second speaker, and lastly, Johan as the last speaker. So, I'm going to quickly jump into the first question before you peeps get more impatient. Firstly, do you know why computers are digital? Computers have become primarily digital and have become an easier use of technology starting from the 30s to the generation nowadays due to the efficiency, reliability, and the flexibility of the machine. Computers have circuits which they only have two possible states, which are known as on and off states, and can be indicated as 1 and 0 respectively. These numbers, 1s and 0s, are known as binary digits or used with the term bit, which it can form a sequence of bits to depict word characters, images, and even multimedia. So, how can a computer represent numbers, words, and letters using bits? Data that consists of only number might only be used in arithmetic operations, but for character data, like letters, symbols, and numerals, do not need to use arithmetic operations. Numeric data in computers are represented by using the binary system base 2, consisting of only 1s and 0s. On the other hand, character data is represented by several types of modern character encoding such as ASCII, extended ASCII, and Unicode. Wait, so what's character encoding in the first place? Character encoding is a system used to represent a repertoire of characters using a form of encoding. The earliest encoding systems included Braille, International Maritime Signals flags, followed by the more modern ASCII, extended ASCII, Unicode, Morse code, and Baudot code. So why is it so important to have this character encoding? English text is the most basic text anyone could understand worldwide, but what if you're reading a full site of languages like Mandarin, Korean, Arabic, Tamil, or even Urdu? Will it be the same like English text? Nope, I don't think so. Instead, a full site garbled text will show up in front of you, and you won't understand even a single word from it due to the lack of bits of the character encoding, and this will be discussed and solved by Johan later on. Okay, so what are the character encodings that people use nowadays? ASCII, which is known as the American Standard Code Information Interchange, has 128 characters that includes upper and lowercase letters, punctuation symbols, and numerals with 7 bits for each and every one of them. While extended ASCII, the word extend means expand, or a simpler word, enlarge. So you know that ASCII character encoding has something added into it to be named as an extended ASCII, or can even be known as a superset of ASCII, which they extended from 7 bits to 8 bits to provide codes for another 128 characters like boxes, circles, and other graphical symbols. EBCDIC, also known as the Extended Binary Coded Decimal Interchange Code, is usually used by older mainframe computers and is different from 8-bit codes. But ASCII and EBCDIC representations could not represent other than English language or alphabets. Therefore, it is needed to use another representation to represent other languages like Japanese, Russian, Chinese, or even Arabic languages or alphabets by expanding ASCII representation from 7 bits to 16 bits, which provides the ability to store more than 65,000 characters. This well-known and commonly used character encoding is known as the Unicode. The first 128 characters in Unicode is the same as the characters in ASCII, but the rest of the characters in Unicode representation which are used to store characters can be found in other languages, along with other symbols like emojis, currency symbols, arrows, and etc. One extra question: since the computer works with a series of 1s and 0s, how does it know which code to use? Whatever performance that the computer works on are stored in files in order to avoid confusion, as it has extremely long sequence bits of ones and zeros, which the machine has to know whether it has to convert to ASCII code, binary numbers, or the codes for multimedia. Therefore, most of the files contains a file header, each with the codes information to represent the file data. So when the computer reads the file header, it knows how the contents in the file were coded. So now I would like to pass the time to Chaman. Thank you.
Thanks, Yoko. Now we mentioned ASCII earlier. ASCII uses fixed length codes which are easy to process and also quite simple. It is strongly advisable that using a fixed set of digits is better than varying lengths. However, it should be noted that it is possible to create an encoding where a symbol is represented by varying numbers of digits, aka variable length encoding. This is actually known to be quite efficient. Now, under variable length encoding comes another interesting subtopic. For this, let us represent the first 9 letters of the alphabet from the numbers 1 to 9. The remainder will be 10 to 26. Now, let us take an example. 25191925. Now, if we decode this, what do we get? Bessie, right? Well, not exactly. What if we were to take the first 2 digits of the first letter? That would make it EIEIBE. Now, makes no sense, but it is quite possible. Or suppose we take another order. So this form of decoding is full of errors. Suppose we take a different kind of sequence. 510 5320. 51 is not included in the scheme, making it impossible. So we will have to encode 5, which is E. Then we have 1 and 0. Since 0 cannot represent anything, then it has to be 1 and 0, which we decode. This is J. Moving like this, you will notice that this sequence will undeniably give us the word eject. So this sequence has no alternatives. We call this uniquely decodable. Now this takes us to a very useful coding scheme, Huffman coding, which is a lossless data compression algorithm. The coding assigned to the characters depends on the frequency that they have been used, which means that only a very small amount of bits will be used. The beauty of this system is that the characters are prefix codes, which means the codes are assigned so that one character is not a prefix or a code to any other character. This ensures that there is no ambiguity when decoding. Let's take an example. Suppose the frequency of characters is as shown, meaning A in this case is used exactly 5 times, B is used exactly 9 times, and so on. With the Huffman coding system, we use the least used characters at the bottom of a diagram and the most used characters at the top, like so. From this diagram, we can set an encoding scheme like this. Compared to the list I showed earlier, you will notice that the most frequently used letters have the least number of bits, which is incredibly useful. Since there are so many types of encoding, we will come across cases where target devices do not support the format, or maybe there are storage limitations, or maybe you just want to convert incompatible or obsolete data to better and improved formats. There are methods made to convert one encoding to another, and this is known as transcoding, which is defined as the digital to digital conversion of one encoding to another, which enables national language support and will help to display HTML files with characters that are not found in the IS or Latin 1 encoding. This is helpful if there are characters outside the known 7-bit ASCII character set. We use this method for movie data files like PAL and NTSC, and even audio files like MP4 and MKV. All the same, we can use it to convert a UTF encoding to IEC and vice versa. So how does this encoding work? Well, the theory is pretty straightforward. Data from one encoding is simply made available in another encoding. It is taken from its native encoding to whatever method is required in the display. First, the native state of your data is determined. Then, the desired displayable state is determined. A transcoding list is then created for these two encodings. This list is what connects the encodings together and then gives what is known as a numeric character reference, NCR, which is used for each character. So let's take a few examples. The exclamation mark, capital A and capital A with a ring above it, are represented by hexadecimal 5A, C1, and 6-7 in their native encoding. In the newly transcoded set, these three are represented by hexadecimal 2-1, 4-1 and C5 respectively. Sounds good, right? Well, this whole procedure is known to have its issues. There are cases where some encodings might use different code points. Sometimes characters in one encoding might not be present in another encoding. This can especially be the case in currency symbols like the euro or the dollar. Let's say encoding method A has a euro symbol and encoding system B doesn't have it. Then system B will likely not show. Much more worse scenarios can include a situation where there is an error in the transcoding and then the data cannot be transcoded back to the original. And from now on, I'll be giving the show to Johan.
Thank you, Chamal. I'm Johan, and now let's see what global text is. Have you ever tried to read a text file on your computer and you saw something like this? Pretty much unreadable for most of us, right? However, this is supposed to be just some characters in a text editor. The primary reason for such phenomenon is that one or a sequence of bytes are being read using the inappropriate encoding scheme. Remember that computers only read, process, and store data in binary, and that characters are represented by a sequence of binary numbers of at least 1 byte defined by an encoding scheme. Now, since there are different characters for different languages, there are different encoding schemes for different character set. The computer has to be told what encoding scheme to use to read or write text. I will demonstrate a very simple example using Notepad. If someone were to write those 3 simple French words that use accent, the encoding scheme has to be the same for the one writing it and the one reading it as well. This text file right now is encoded in UTF-8 and can be thought of as the writer's text. Now, when the encoding scheme is changed to ANSI, for example, which can be thought of as the reader's text, what the latter sees is garbled text. UTF-8 is an encoding that applies to the Unicode character table. It uses the ASCII character as the de facto baseline and represents them using a single byte, whereas extended ASCII characters and others can take 2 bytes or more. Using the Unicode UTF-8 table, I have written the code point and the hexadecimal of the 3-letter word here. The hexadecimal representation can be converted into binary to obtain the sequence of bytes that represents each character. The bottom part of the whiteboard shows the bit sequence for the word encoded in UTF-8. The computer only knows this bit sequence. Now, when ANSI is used to decode the bit sequence, the process is done based on the ANSI table or code page. ANSI has a character set that includes the standard ASCII character plus extended characters and uses only a single byte. Therefore, if this bit sequence here is decoded under ANSI, the first bit will be translated to this character. The first byte, the second byte here will be translated to this character. The third byte, being an ASCII character, will remain the same, so on and so on. Finally, decoding this bit sequence in ANSI will lead to these characters. As we can see, the original data changed, and this is garbled text. The process is similar for the other words. Since we know that the UTF-8 and ANSI share binary compatibility for all ASCII characters, we are only going to concern ourselves with the hexadecimal and binary sequence of the non-ASCII characters. Here is the binary sequence of the UTF-8 encoded text. And again, when the UTF-8 encoded text is decoded in NSI, the binary sequence is translated into the character based on the ANSI table. And the 2 bytes special characters yield 2 other 8 bytes characters that are as follows. This is the binary sequence of the 2 8-byte characters. A person reading the UTF-8 encoded word using ANSI will see this garbled text. Just like some characters encoded in UTF-8 yields garbled text when decoded in ANSI, there are other encoding schemes that do not support character set of the others and will give garbled text unless The same encoding format is used to decode that text. Some text editor may discard any bytes that are not valid in the chosen encoding or replace them with a question mark, or replace the character that couldn't be decoded with the Unicode replacement character. In the case where a gobble file was received or opened with no information about the source encoding, character encoding detection or character set detection can be used. The latter is the process of finding out the character set or encoding of a character data in an unknown format. The process makes use of statistics and heuristic, but is known to be not very precise, and also requires hundreds of bytes of character to be fed in a single language to be able to determine the encoding or character set of the latter. There are different techniques that are used. For example, for single byte encoding scheme, the data is checked against a list of most frequently occurring free letters group for a particular language. And for multi-byte encoding, the sequence of bytes is checked for legal patterns, and the detected character set is also checked against a list of frequency used character in that encoding.
Okay, that will be for the video tutorial.
Hope you would enjoy the video.
And we hope to see you all in class.
See you.